Hello everyone, and welcome to our presentation on Big O for common algorithms. Today, we'll be discussing algorithm efficiency and complexity, and how BigONotation helps us predict performance and scalability. We'll cover the definition and importance of Big O, review common algorithmic complexities, and use visual comparisons and real-world examples to illustrate the concepts. Let's get started. BigONotation is a way to describe the upper bound of an algorithm's running time. It abstracts the growth rate of an algorithm's runtime as the input size increases. The key points to remember are that Big O focuses on the worst-case scenario and ignores constants and lower-order terms. This simplification makes it easier to analyze performance and guides us in choosing and optimizing algorithms. Constant time complexity, or O1, means that the execution time of an operation remains constant, no matter how large the input size gets. For example, retrieving an element from an array by its index is a constant time operation because it takes the same amount of time regardless of the array size. Please refer to the visual demonstration on this slide, which shows how an array allows for fixed time index access. Next, we have linear time complexity, or ON. Here, the execution time increases directly proportional to the input size. This is typical in operations that involve a single loop, such as scanning through an array to find a specific value. As the number of elements increases, the number of operations grows linearly. On the slide, you'll see a visual that illustrates a loop iterating through a list. Quadratic time complexity, or O(n squared), means that the execution time is proportional to the square of the input size. This often occurs in algorithms with nested loops. For example, in the worst-case scenario of sorting algorithms like bubble sort or insertion sort, the performance degrades rapidly as the input size increases. Here you will find the visual demonstrations of all the time complexity. You will find all the animation for different complexity. Here compares the number of iterations in nested loops to help you understand the quadratic growth pattern. There are several other complexity classes we should be aware of. Logarithmic time, log n here, the problem size is halved at each step, as seen in binary search. Linearithmic time, n log n. This combines linear and logarithmic growth, which is typical in efficient sorting algorithms like merge sort and heap sort. Exponential time, 2 to the power n. In these cases, the number of steps doubles with each additional input element, common in some recursive algorithms. Factorial time, n. This represents extremely slow growth, often observed in brute force solutions, such as those used in the traveling salesman problem. Each of these classes has its own characteristics, and they affect algorithm performance in different ways. In this section, we compare how different Big O classes scale with increasing input sizes. You'll see graphs that plot time complexity versus input size, with comparative curves for O1, n log n, n squared, and 2 to the power n. The key insight here is that while constant and logarithmic time complexities remain flat or grow very slowly, linear and quadratic complexities increase at more noticeable rates, and exponential complexities become impractical with even modest increases in input size. Please take a close look at the animation which is running over here, and you will notice all the complexity representation in action. To summarize, BigONotation is essential for understanding algorithm efficiency. We've reviewed common complexities, including constant, linear, and quadratic time, as well as logarithmic, linearithmic, exponential, and even factorial growth. These visual comparisons help us grasp how input size impacts performance. As developers, it's crucial to choose algorithms based on expected input sizes and to consider trade-offs between simplicity and efficiency. Now, I'd like to open the floor for questions and further discussion. If you have any questions, then please write in comment section. Thank you for your attention, and let's explore any questions you might have.